Okay, so this first subtraction is minus 5 times 4 factorial. So first of all, where did the 5 come from? Well, it's because there are 5 separate rules, which we can still see above. 5 forbidden outputs. Phi of 1 does not equal to 3. Phi of 1 does not equal to 5. Phi of 2 is not equal to 3. Phi of 2 is not equal to 4. And phi of 5 does not equal 4. So those are 5 sets of permutations which I need to subtract. The thing is that each one of them is defined by fixing one output. So you fix one output, and then you have 4 factorial ways to finish making the permutation after you fix the output. Well, that means I'll be subtracting 4 factorial 5 times. And I just decided to write it the fast way. 5 times 4 factorial. Now, let's move to the next one, which is more complicated. When I want to add back in ways of breaking 2 rules at once, these are the intersections of sets of forbidden permutations. And an intersection of 2 of those would be a collection of permutations where we're breaking 2 rules. So every time I break 2 rules out of these 5, what that means is I'll be sending input for 2 of the inputs to 2 forbidden outputs. And that means I'll have 3 more inputs to finish up. 3 inputs to finish up, I can always do it 3 factorial ways. There's still three inputs and 3 more outputs, and so I pick the first one, the second one, the last one, and that gives you 3 factorial. So how many ways are there to break 2 rules? Since I know I'm always going to finish them up by counting 3 factorial, all I need to know is how many ways there are to break 2 rules. Well, typically, out of 5 forbidden sets, there should be 5 choose 2, which is 10 intersections. But as you can see, there's only 6 here. That's because of the principles of permutations that we looked at. The fact that they have to be functions and they have to be one-to-one. First of all, they have to be functions. That means I can't break the first 2 rules simultaneously. Phi of 1 does not equal to 3 and phi of 1 does not equal to 5. If I try to break them both at the same time, I'll be sending 1 to both 3 and to 5, which is not going to happen. So immediately I realize the only way to break 2 rules is to break rules for 2 different inputs. I look at my list of 5 rules that I'm supposed to try to worry about, and there's only 3 inputs. There's phi of 1, phi of 2, and phi of 5 at the end there. So that narrows it down. I only have to consider 2 inputs, 2 different inputs at a time. So out of the 3 there, I know there's going to be 3 possibilities. 3 choose 2. So I can try breaking rules with input 1 and 2, input 1 and 5, and input 2 and 5. So that's why I've drawn 3 little trees. These are decision trees, and in the small square is the input. So for each of them, I've chosen 2 of the inputs that I need to worry about. For that first tree, I choose input number 1 and then input number 2. For the second tree, it'll be input 1 and 5, and for the last tree, a little hard to see, it's input 2 and 5. Those are in the little boxes. And those are the decisions. To break 2 rules, for instance, on the first tree, first I need to figure out how to break rule 1. That I can do by sending phi of 1, making it equal to 3 or to 5. And then, for the second decision, I break a rule about input 2. Now, for input 2, there's 2 things that I could do to break it. I could send it to 3 or to 4. However, if I already sent input 1 to 3, I can't send input 2 to 3 as well, since that would not be one-to-one. So on that top, there's only one possible choice. It depends on what I picked for input 1. I can only pick input 2 to be 4. If I picked input 1 to be 5, then I can pick input 2 to be 3 or 4. So on any path from the left to right of these trees, you can only see the numbers appearing on those little edges. Those are the outputs. You can only see one of each on any path from the left to the right, from the root to the leaves. Otherwise, you'd be breaking the one-to-oneness. You'd have two outputs. You'd have two inputs going to the same output. And so the leaves at the end of the tree represent breaking two rules. At the top there, I just reiterate that top leaf is phi of 1 equal to 3 and phi of 2 equal to 4. You can look at the rest of them. The next leaf down would be phi of 1 equal to 5 and then phi of 2 equal to 3. And then the last leaf would be phi of 1 equal to 5 and phi of 2 equal to 4. So there's only three ways to do that. And next, we look at input 1 and 5. Same choices for input 1, but there's only one choice for input 5. And it didn't have any trouble with one-to-oneness, so I get 2 there. And then last, I look at input 2 and input 5. There's two choices for input 2. It could be 3 or 4. Input 5, however, can only be 4. And that means there's no way to continue the tree on that lower branch. I just put a little X because I'm not allowed to put another 4 on that path. But I can put it on the top one, so I get one more possibility. And then counting those leaves, the circle, bigger dark circle leaves, 1, 2, 3, 4, 5, 6. That's where the 6 comes from. Then next you try and break 3 rules at a time. It turns out there's only 3 inputs, so there's only one possible tree. There's no way to choose 3 inputs, 3 rules any other way. I have to choose one from each of the inputs because it's a function. So I put rule 1. You can choose to make the output 3 or 5 to break the rule. Then input 2, the output can be 3 or 4, but it can't be a 3 if I already chose a 3 in the first choice. And then rule 5, that's rule 5 there, the third decision. Again, the only way to do that is to make it a 4, so both the top and the bottom branches end there. Can't put a 4 twice. So there's only that one middle branch that finishes up all 3 ways, and that's the only leaf. There's only one way to break 3 rules at a time. And then 2 factorial comes from the fact that after you break 3 rules, there's still 2 more numbers out of 5 to choose outputs for. And then there is no way to break 4 rules. And in this case, that comes from the fact that there's only 3 inputs mentioned in the 5 rules. Look at them again. So there's no way to break 4 rules without not being a function. Same for 5 rules. And that's the total. And it ends up pretty easy to calculate. It comes out to 34.